Let us look at the fourth order polynomial and try to express it as a function of its derivative. But to succeed to do that, you might need to transform it first. So we will explore to find out what transformation might be needed first before we can express it as a function of its second derivative. So the second derivative of the fourth order function is a quadratic function. So that's what we have here. After differentiation, now you can label it P4 double bar. Oh, sorry, I had squared it, so it's still P4, it's not squared. Sorry for the mistake. So it has order 4 when you square it, because the goal is to see whether we can transform the fourth order polynomial and express it as some polynomial function of its second derivative. So that's why I squared it here. So now if you expand this expression, you will get these results. So you can work out these on your own. You have to do some interchanging of limits so that you can, instead of having these two powers for the variable v, then independent variable, you can express the powers in terms of one index. So that's basically what happened here, the work of interchanging limits and so on, and getting the final coefficients. Now we can proceed to see what happens when we calculate the resulting coefficients from their expressions. So we get that this, after we square the derivative, this coefficient of P bar is 144, and likewise we have the other coefficients calculated out explicitly. So Q3 is just Q3 bar is just Q3 with 144. So you see that P bar is similar to P for the first two terms. If you scale by 144, you get P4 bar for the first two terms, but the other terms have something else. So we are going to see what to do about them. So you have this for Q2 bar, and you have this result for Q1 bar, and this result for Q0 bar, and I summarize P4 bar with its expression. So given that we have P4 bar, we can go ahead to just make another label, P4 tilde, in which we divide out the 144 coefficient, and then that makes v to the power of 4 have a coefficient of 1, and of course you have the q3 from p4, the original polynomial. So this is the main similarity, and the rest are different in their expression. Now we can take the difference from the original polynomial p4. Now it's nice if you can set q4 bar with q4 equal to 1, because then you continue with a coefficient of 1 at the maximum power. And that is done by initially dividing all the terms by q4 if q4 was not 1. Now, but I'll just keep doing these calculations leaving q4, because these expressions were generated from the previous formulas. So here we go again and rename this difference. Then you divide by the leading coefficient for the highest degree here to get this. So we can now compare this result, which is another quadratic function, to the second derivative of the original fourth order polynomial, and try to deduce a condition that will enable us to express the fourth order polynomial as a function of its second derivative. So that condition is this: just enforce that this coefficient q3 is equal to, that is q3 over 2. Here it is that it is equal to the coefficient of the same order. Where is it? Right here, of the same order that you have in the other polynomial here, right here. So the order is 1, v to the 1. So the coefficient for the order v to the 2 is 1 by dividing out. Now we want to force this right here to be equal to this. Then all you have left to do is to just add some equalizing shifts. So once they are equal, you have this condition which is forcing q3 to be 0. So if you translate p4 such that q3 is 0, then you can have this equality. If you have this equality, then we can express p4 as a function of its second derivative, which is a quadratic. So that's one way to solve for the roots of a fourth order polynomial.